Okie doke. That's a sign and sheet around. How is everybody doing today? What are we going to focus on today aside from everything? Anybody have anything in particular that you want me to pay special attention to? Nothing? Okay, perfect. No. If you are worried about limiting reactants, so you can basically take the same first however many steps and just substitute the last step in to determine whether you're trying to calculate how much of product A or product B is produced. We'll do this example, which will cover that. So we'll open with this example, and then we will bust through as much information as we can. Because you have a test tomorrow, I'll be covering a lot of information fairly quickly. So if you have any questions, please stop me in some egregious manner if I don't turn around and see you waving your hand. Sound like a plan? Nothing that anybody wants to focus on except this one question here? Yeah. Okay. All right. So 5.7 grams of butane are combusted with 9.4 grams of oxygen gas. How many milliliters of water are produced? Anybody want to take a stab at what we're going to do first? Anybody that was here Tuesday should know the first two steps you should always do. Right. So first we're going to determine our reaction and or formulas. Okay. So let's do that. What is our reaction? Well, first we need to figure out what we have. Anybody want to take a stab at what we have here for our reaction? Okay. All right. Perfect. What's butane? B4H10. So, how do we know that? Well, if you think back to your hydrocarbons, remember we named those off of the number of carbons that are present and the types of bonds that you have. So, remember that the number of carbons, prefix, you start with methane, so meth, then F, so bute, pent, and then we follow your typical prefixes from pent through depth, right? Pent, X, F, ox, no, and depth. So I did that. 1, 2, 3, 4, 5. The other way we name our hydrocarbons is off of the types of bonds that are present. So we have ane, ene, and ine. What do those respective suffixes mean? All right, so your anes or your alkanes have all single bonds. All single bonds. Your enes have at least one double bond, and your ines have at least one triple bond. One double bond and at least one triple bond. So we're dealing with butane, that means we have 4 carbons. In this case, for you guys' purposes, you're only ever working with straight chain hydrocarbons, so nothing branched off. And we can identify that we're going to have 10 hydrogen a couple of ways. We can either draw it out, count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or you can remember that for your alkanes, it will be 2 times the number of carbons plus 2. 2 times 4 plus 2 gives us 10. We have C4H10 plus our O2 gives us CO2 and water. What is our next step? Balance it. So we're going to set up our table here of reactants and products. CHO, that order is going to work the best. Remember to have whatever is by itself be last, regardless of what you're balancing. So in this case, we have oxygen by itself, so we're going to put oxygen last. Because if we change the number of O2, we don't affect anything else in the reaction. If you set it up correctly, you'll always get 1, 2, 3 on your product side. For our reactant side, how many carbons do we have? 4, 10 hydrogen, and 2 oxygen. Now we can go down the line and start balancing. So we have 4 carbons on our reactant side, 1 carbon on our product side. We'll go ahead and add a coefficient there and make that 4. We balance our carbon, but we also change the number of oxygen that we have. So how many oxygen do we now have on our product side? 9. Everybody good there? 9. So our carbons are balanced. We move on to hydrogen now. We have 10 hydrogen on the reactant side, only 2 on the product side. So we're going to put a 5 here. So our hydrogen becomes 10. Now how many oxygen do we have? 13. 13. Well, that's tricky. Anybody remember what you're going to do to get around that problem? Double everything. Well, first, let's figure out how many oxygen we need before we double everything. So we're going to say we have 2. We need 13. 13 divided by 2 gives us 6.5. So temporarily, we're going to say that we have 6.5 oxygen. Now, you know that you cannot have fractions for your stoichiometric coefficient. So we're going to multiply it through by the denominator. So through here, denominator is 2 because we have 1/2. Multiply everything times 2. Then we're going to go in and say we have 10 water, 8 carbon dioxide, 13 oxygen, and 2 of butane. Is everybody good there? Fantastic. So we have finished our first step, determine our reaction. What is our second step that we always do with problems like this? Something that you should probably do for every single chemistry problem that you see. Well, yes and no. What do we need to do for our second step? Always, 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 always. Can I compare grams of butane to grams of water directly? Yes, no, no, yes. Anybody got any ideas? We're going to do this one in red. So, we can never go grams to grams. We cannot go from grams of one thing to grams of another thing. But what we can do is go grams to moles, and then moles to moles, and then moles back to grams. Whenever we're given 2 things in grams, we have to convert them to moles. So, we are told that we have 5.7 grams of butane. How are we going to convert that to moles of butane? Molar mass. How do we determine the molar mass of something? grams of butane. 5.7 grams of butane. Remember your molar mass is equal to the atomic mass. We go over the periodic table, and we find that the molar mass of carbon is 12.01, and the molar mass of hydrogen is 1.01. We have 4 carbons. We have to multiply this times 4. We get 48.04. And we have 10 hydrogens. Multiply this times 10. We get 10.1. Together, we get 58.14. So 58.14 grams per mole of butane. Fantastic. So we know that we want our grams to cancel, and we're left with moles. So we're going to put our grams in the denominator, 58.14, and 1 mole on top. Now we're left with moles of butane. Moles of butane. Anybody have that number? Anybody have a calculator? You all have a calculator. Approximately 0.1, 0.098-ish. Zero point 0.9098 moles of butane. Right? So now we know our moles of butane. Let's continue converting the moles. Our other mass we have is of oxygen. So if we have 9.4 grams of oxygen, we're going to do the exact same thing we did with butane, but for water. You'll also start to memorize some of these. So we know water is 18.02 grams per 1 mole. Does anybody want me to go through and calculate that? No? Okay. So we do this, and we get, what, 0.52-ish? Try that again. You're off by after time. I went forward about 18.2. Just over half. 9.4 out of 18.02. So we get 0.511. On the same page there. So now we know how many moles of butane we have and how many moles of oxygen we have. What are we going to do with that? Once we get to this point, there's a couple different ways that we can do this. Some of it comes down to personal preference. How you want to do the math. So we know our molar ratios of product to reactant, right? So let's say we have butane, and we're asked how much water is produced. Right, so I know that I have 0.098 moles of butane. And I know that if I react that with excess oxygen, so I'm going to react all of my butane. If I react all of my butane, I know that we produce 10 moles of water, 10 moles of H2O for every 2 moles of butane. Does everybody see that? All right, so we go through and calculate this. We get 0.5-ish, yeah? 0.49. 0.49 moles of water. Right, so that means if we were able to react all of our butane, we would produce about a half a mole of water. We can do the same thing for oxygen. So we know that we have 9.4 grams of oxygen. which is about a half a mole. So we have 0.511. Five, two, two. Up here?
Yeah.
Oh. How many of you caught that? I did say. I have 3 bouncy balls in my hand. Not a third thrower. Exactly why I'm not sure. All right, so this was actually 0.49. Yeah. I told you it was going to be 5.2. 0.49. All right, 0.49 moles of water. So now we go back down here. We have 522 moles of oxygen. We're going to convert it the same way. So we know for every 13 moles of, well, back up a minute. I'm sorry, guys. So, everybody catch my mistake? Get bonus points, even though I can't get all points. We'll get to that soon. I made an error probably about 5 minutes ago. Anybody catch it? Anybody catch it? Alex? What's your question? Oh, this would do. So, I took 9.4 grams of oxygen and I divided it by the molar mass of water. That's the problem. We should divide by the molar mass of oxygen. Hey, don't you think? Okay. So, we're going to change the factor to number again. Alright, so we're going to take our 9.4 divided by 16 times 2. So we're actually dividing by 36. Right, because oxygen gas is O2, each oxygen has a molar mass of 16. 16 times 2 gives us 32. And we get what? 0.24? 2.29, like you said. 9.4 divided by 32. 0.29. 0.29. Okay. So 0.29 is 0.294. So that's how many moles of water we have. 294. 294. So we're going to divide that by 13. Not really. We know that every 10 moles of water that are produced, we consume 13 moles of oxygen. So I'll multiply this times 10 over 13. And what do we get? .226. What this means is if we reacted all of our water, we would produce 0.226 moles. If we reacted all of our oxygen, we would produce 0.226 moles of water. Whereas if we reacted all of our butane, we would produce 0.49 moles of water. So what is our limiting reactant? Oxygen. I don't know how that happens. We have a chamber where we only let a certain amount of oxygen in. So we determined our oxygen to be our limiting reactant. Because we will use up all of the oxygen and still have butane left over. Does that make sense? So when we finish the rest of this problem, we are going to use moles to milliliters. How are we going to get there? I like what both of you were thinking. You would produce water as a gas. we're gonna say after condensing. Right? So we're gonna burn this, we're gonna produce a bunch of vapor, and then we're gonna cool it down and condense it back into liquid water. But I like where you guys were going. Okay, so after we condense it. So what is another way to do it? Rather than convert from moles to liters, assuming it's nitric acid. You all know how to do this. Anybody want to take a stab at what we're going to do? I promise you, you all know how to do this. We have moles of water. We have to get to liters. Take it to grams. Okay? Take it to grams. If you don't know what to do, start changing your units. For real. If we were just given this and we didn't know what to do, well, we know we can convert grams to moles. That's a good first step. Right? And now we're towards the end of the problem, so we should probably convert it back out. So we have 0.226 moles of water. How are we going to convert that to grams of water? Molar mass. And this time we're going to use water. So 18.02 grams. What does that give us? 4.4-ish? 4.07. Where's 4.07 grams of water. We have problems. We have problems. That will do it. Remember that when you are going moles to grams, your number should go up. Go up because every single thing that you're working with will weigh more in grams than it does for the number of moles. Because even the smallest thing we know on the atomic scale is hydrogen. Hydrogen has a molar mass of 1.01 on average. So your number will always go up converting from moles to grams and always go down if you're going the other direction. We have 4.07 grams of water. How do we go from grams of water to milliliters of water? How do you convert mass to volume? Density, right? So you know that density equals mass over volume, right? And some of you might have learned some fancy triangle things before you, right? Anybody know what I'm talking about? I do. So if you cover a density, you get mass over volume. If you want volume, you get mass over density. Yeah, I don't know. Anyway, so we know that what is the density of water? Yes. You all should know that. 1. Kind of, not really. If it's liquid water, it will always be basically 1. We get 1 mil per 1 gram. So we get 4.07 milliliters. That is your final answer. Any questions on this example problem? 1 gram. This step or this step? Oh, yeah. 1 mil per 1 gram. So your mils cancel, your grams cancel, you're left with mils. Moving. Can anybody not see red in here? Great. I've only wrote a small amount. Okay. Does that answer the limiting reactant question that you had? Yeah. Okay. Cool. Has everyone memorized their polyatomic ions? Or are you all just planning on cheating during your test? No answer. Okay. I know. I know. Wonderful. All right. All right. Half an hour left. So, does anybody care to cover follow-up? Raise your hand. General definitions, chemistry, matter, mass, weight, mixtures, homogeneous mixtures, SI base units, prefixes, giga, tetra, milli, centi, so on and so forth. Significant figures. Sig figs, okay, cool. History. Who did what experiment? Yeah. One of my favorites. What did that determine? No. Nope. And we also want to take a stab at what the gold foil experiment accomplished. What did it do? What did it prove? What did it replace? Yes. What model did that replace? From pudding model. So we at first thought that atom looked like this, with little electrons all over. Yep. And then Rutherford said, "Hey, shoot this piece of foil with this detection device that he found that we got a lot of responses out here, and every so often he would get one that was deflected." And so what he deduced from that is that we have the nucleus and the electron cloud, and so what he was observing is that most everything passed straight through unless it hit the nucleus in which it bumped up. Okay. Photon. Bursts of energy, basically, without getting into too much of it. Okay, so we'll talk some about sig figs. Naming. Covalent compounds, ionic compounds, polyatomic ions. Balancing reactions. So we're good. That example here of everything that we had questions on balancing. Naming acids and bases. Yes. Okay.
Actually, could you go over that one?
Yes. Calculating concentrations. So mostly naming stuff, yeah? Covalent, ionic, acid, bases, diatomic, sweet. One naming question. There's a lot of different things you can name. How many total questions? How many total questions? 120 questions and only one is on naming? I'd have to imagine multiple choice will also do it. All right. With that, do we still want to talk a lot about naming and different things? Yeah. Naming. So, you have your covalent compound. Covalent. And when we name our covalent compounds, we're going to name them as prefix atom, prefix atom. The prefixes for this are covalent compounds that are not your hydrocarbon chain. Going to be mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Everybody good there? A couple of nuance rules with this is that we drop double vowel sound and drop mono before the first atom. So what would be the name of SO2? Sulfur dioxide, right? We have one sulfur, so initially you might think mono sulfur dioxide. Remember, we're going to get rid of that mono. We get mono sulfur, or we use sulfur dioxide. Right? Okay. What if we had N2O4? Dinitrogen. What was the second part? Tetroxide. Dinitrogen tetroxide. What about NO3? I don't know. Is it an ion? Does it have a charge? Not here. Nitrogen trioxide. Be careful with your polyatomic ions. If they are not ions, if they're not charged, they are just covalent compounds. Any questions with this naming of covalent compounds? The only other covalent naming that you are likely to see, we already talked about, but cover again, is your hydrocarbon. Hydrocarbon. So In this case, we have our prefixes 1, 2, 3, 4. So we have meth, soap, bute, and then the same 5 through forever. Remember that you start off with those 4 that are different. Your endings are determined by the type of bonds. We have ane for our alkanes, ene for alkenes, and kyne for our alkynes. Remember that those go in order of your vowels. So A, E, I, O, U, and sometimes Y is the same order for increasing bond strength. Any questions on that? Nope. All right, fantastic. Next for naming, we will talk about ionic compounds. So your ionic compounds, we are going to name, remember, without prefixes because the charges are fixed. We're going to name them with cation and anion, ide, or the name of the polyatomic ion. Does that make sense? We are never changing the name of the cation. We only will change the name of the anion. So if we have sodium and chlorine together, our cation is sodium. We're going to name that first. We would have sodium. Chlorine becomes chloride. So we would have sodium chloride. We also substitute in the name of a polyatomic ion. So if we have sodium sulfide, we can also have sodium sulfite or sodium sulfate. Does that make sense? Perfect. Remember, you do not have prefixes for ionic compounds because the charges are given and they're only going to come together at that ratio. The only caveat you have with ionic naming is for your transition metals. And so if we look at groups 1, 2, 3 through 8, we know the charges off of their location in the periodic table. So your sodium and magnesium, you know, we're going to be +1 and +2 respectively. Boron will be +3, carbon can go either way, so on and so forth as we go over to our nonmetals. However, if it's not in one of those major 8 groups, we have to identify the charge. So if we have Pb and SO32, what would be the name of this ionic compound? You say lead or sulfite. Anybody have any other suggestions, or is this good to everybody? Remember, we can use the crisscross rule when we're going from our ions into our ionic formula, but you have to be careful because remember that ionic compounds are always written in the most simplified form. So if we were to do this backwards and go, we would get Pb 2 plus SO3 minus. Problem there, we know that sulfite has a -2 charge, so that would have to be 2, so this would have to be 4 to get a 1-to-2 ratio once we form the ionic compound. Any questions there? Does that make sense to everyone? Fantastic. And the last naming that we have will be acids and bases. So for your acids, if we have ion. We'll name it with hydro, whatever it is, ic acid. If it is a polyatomic ion ending in 8, we have whatever it is, ic acid. And if we have our polyatomic ion ending in ite, we have whatever it is, is acid. Does that make sense? So we can have H3P, H3PO3, and H3PO4. What would this first acid be? Very good. Hydro, phosphoric acid. We have phosphorus, that's where we get the phosphor. It is not a polyatomic ion, so we have hydrophosphoric acid. How about the second one here? H3PO3. Phosphoric acid. Any other suggestions? You say it's good. Yeah. Very good. This is going to be phosphorus acid. And these are in a different order than these are. Because your PO3 is phosphorite. PO4, I'm sorry, is phosphite. PO4 is phosphate. So what is our last acid? Phosphoric acid. Very good. This is particularly important if you're working with reactions and you're given that maybe hydrophosphoric acid reacts with calcium hydroxide. Important that you can identify that that's just H3P, not one of your polyatomic ions. Moving. As far as naming bases, you guys and what you guys have covered, that's much easier because your bases have hydroxide. So you're just going to name them as any other polyatomic ion. That makes sense. So you have sodium hydroxide, that will be the base because your OH is a Bronsted-Lowry proton acceptor, as we saw with the acid-base reaction that we did in previous sessions. So you're just going to name them the same: calcium hydroxide, sodium hydroxide, magnesium hydroxide, etc., so on and so forth. Any questions there? Any questions on names? We have 10 minutes left. What do you want to talk about? Anything about it? Do you have a specific example in mind? No. Um, Here's what the perfect limit is. Has she given you a threshold? Okay, so the question was about the grub test. Anybody remember what the grub test does for us? It defines what counts as an outlier. That being said, your Grubbs test statistically is determined by how big your sample size is, what your thresholds are, what your confidence level is, which are a lot of statistics that you won't see until you take statistics. As a general rule, your first step will be determining how many standard deviations a value is away from the mean. Right? So if you have, let's say, some distribution, right, and you have a mean that falls at 50. Great. Perfect. Your mean falls at 50, and you take a bunch of measurements, you get a nice curve, and you end up with 70, 90, and 120, or 120, 110, and you get the same thing on this side, so you get 30, 10, and for the sake of negative measurement. Maybe we're measuring temperature, and we're not really good at it because this is a really wide range. So let's say we get a particular value. Let's say we get 51, 49, 72, negative 15, and 4. You determine which of these counts as an outlier. And for this sake, I'm going to say that an outlier is greater than three standard deviations from the mean. Well, you would go through and say, well, I know my standard deviation here is 20. That would be given. Your standard deviation is 20. So here we can take 51 minus our average, which is 50. So it would be x minus your x bar, which is your mean, minus 50 divided by your standard deviation, which is 20, and you get 0.05. So that's pretty close. Go through and do these for all of them. Right, really what you're calculating here is your z value, but we can use this to help determine where our outliers are. We do this down the line, and when we get to negative 15, we get negative 15 minus 50 gives us 65 over 20. That gives us negative 3.05. That is greater than 3 standard deviations away from the mean. We would define that as an outlier. Is that clarified? Perfect. This isn't really the true Grubbs test, but for your purposes, you're going to be determining if something's an outlier based on how many standard deviations it is away from the mean, regardless of your sample size. Cool. I told you I talked about significant figures, but I forgot. So we will real quick talk about sig figs. Sig figs. Do you want to talk about identifying how many sig figs are in a number, or more computational stuff? All right, fantastic. So I doubt you'll see a lot of questions on this. After this test, you certainly won't see any questions on it until you take the ACS final, in which they might ask you a handful of questions about sig figs, but those questions will only have to do with sig figs. And every other calculation you do on the road, except very specific ones in lab, you can basically ignore sig figs. Okay. Unless you are asked about sig figs, don't worry if it's a free response answer. If you have one extra or one fewer sig figs, obviously, if you're given very broad numbers that end in a lot of zeros and you give 15 decimals, well, that's probably a problem. And if you round to the tens place on a number, that's also probably a problem. Okay? So, your sig fig. Sig fig. Number one rule, your non-zeros are significant. for your zeros. The zeros are not significant when they are leading zeros. Right? You can put as many zeros in front of a number as you want. It doesn't make them significant. They are significant when they are, quote, sandwich zeros. So if they are between two non-zeros, they're significant. So if we had 1, 0, 0, 0, 0, 0, 1, 2.4, all of those numbers are significant because your non-zeros are significant and your zeros between two non-zeros are significant. Next we have n zeros to the right of your decimal. So 1.0000, those are to the right of your decimal. They are significant. Does that make sense? Now, you do have to be careful because this rule precedes this rule. So if you had 0.000012, those are still counted as leading zeros and are not significant, even though they're to the right of your decimal. Does that make sense? Yes.
But what about after that?
What do you think? How many sig figs? 4, 4, 4. As a general rule, they are significant. Good question. So our next rule are that n zeros to the left of the decimal, we're going to say are complicated. They're complicated because you can note them different ways. So if you write 100 dot, I don't like this notation, most people don't. Anyway, that would have 3 significant figures, right? Because we're going to treat this as though they're sandwich zeros, right? That decimal says, hey, they're all significant. But if we just, so if we have 100, that would have 1 significant figure. But we can also write 100 a few different ways, right? We can write this as 1 times 10 to the second. That's 100. Right? How many sig figs does that have? 1. What if I wrote this as 1.0 times 10 to the second? That's still 100. But now we're going to have 2 significant figures because we're going to treat this as 0 to the right of the decimal. And likewise, we could have 1.00 times 10 to the second. That would have 3 significant figures. We can keep adding zeros and it's still going to increase the number of significant. Any questions on sig figs? Any questions on anything we talked about today? Any questions on anything else in chemistry? Any questions about anything else, period? No. Was this helpful? Yes, fantastic. I am working on getting a classroom. I have a request in. Apparently it takes a while for them to get their shit together and give me a classroom. Anyway, especially as the number of you guys increases, it'll be important. I will keep you updated whether I tell you in class or I have Dr. Tamorian tell you in class or if I send an email or if I first send an email. Regardless, I will make sure that you know that we will be in a classroom soon. Sweet. Sweet. You all have a good night. You're welcome.